Yeah.
Okay. So today we're happy to have Ayelet Lindenstrass from Indiana University, whose talk is titled Loday Constructions on Spheres and Tori.
Okay, so thank you for inviting me to speak on this seminar. So I want to talk about Loday Constructions on Spheres and Tori. And so the setup is I'm going to take K commutative ring, and I'm going to look at a commutative unital K algebra. And then there's a functor that you can define from finite sets to commutative K algebras that sends the finite set X to a tensor product indexed by X of copies of A. And then that's a functor. If you have a function from two finite sets, then it defines a map on monomials, sending a monomial of a product of A's to a monomial product of B's, where over every point in Y, the coefficient is going to be the product over all the X's that map to Y of the coefficient you had over that X. And of course, it's a unital algebra, so if there's an empty set of X's, it's 1. And if you think about it, okay. And then, so this is what I do for finite sets, and for simplicial sets, I can just apply it level-wise. And then I have the structure maps of the simplicial set, DI and SI, and they satisfy some simplicial relations. So they induce maps between the Loday constructions of the levels. And because the original DI and SI satisfy the simplicial relations, so do the induced DI and SI. So I get a simplicial set L of X. And I can also do this, and that's the thing we call the Loday construction. And this generalizes the commutativity is really important because you see when I do the product over all the X's that map to Y of the coefficient I had at X, then a priori I don't have an order of them on them. So if it's commutative, I don't care. But the fact that it's a ring doesn't really matter. So if, for example, I take K as a commutative ring spectrum, for example, the sphere spectrum, and then A is a commutative K algebra spectrum, I could also do this for spectra. Also, in the case K discrete, I can also do this for simplicial commutative K algebras. And the idea is that, yeah, if I do this straightforwardly, I get a bisimplicial set, but I can take the diagonal, I can get a simplicial set. So that's the Loday construction of a simplicial commutative K algebra. And there's some basic properties that, that we have. So the first one is easy to check level-wise, and therefore it's true. If I have two simplicial sets and I have a common subsimplicial set of both of them, I can glue the two simplicial sets along the subsimplicial set. And if I do the Loday construction over that glued union, that's the same as the Loday construction on one of them, a tensor over the Loday construction of the thing I glue on with the Loday construction of the other. And the point is that level-wise, right, you have the tensor product over all things in the union of Xn joined along Zn with Yn. So that's like a tensor product over Xn tensored along the tensor product over Zn with the tensor product over Yn. So that's a gluing property. A harder property is, but a very important one, is that the homotopy type of the Loday construction, the realization of the Loday construction. So it's a simplicial commutative K algebra, simplicial commutative K algebra spectrum, but you can realize it. And so the homotopy type of the realization is a homotopy invariant of the realization of X. In particular, people often look at the homotopy groups of the realization, which this is a simplicial abelian group. So it's the homology of the simplicial abelian group with the boundary that's the alternating sum of the DIs. And of course, if the homotopy type is a homotopy invariant, so are its homotopy groups. And the final thing is what happens if we iterate this. So I said that I'm willing to do Loday constructions of simplicial commutative K algebras. And so if I take A, and I do the Loday construction over Y of A, well, that's a commutative simplicial K algebra, and then I could do the Loday construction over X of that. And again, that's by simplicial, but I take the diagonal. And so what ends up happening is in dimension n, I really have a product over xn of a product over yn of copies of A, which is the same as the product over copies of xn cross yn of A. So again, this is true level-wise, and therefore this is true. So the easiest examples are, you could take finite sets, and then you can get from A to tensor copies of A. But there is a non-trivial example that we know. And so the interesting space we look at, the simplest non-finite space, I guess, that we're interested in, is the minimal model for the circle, which has one non-degenerate zero simplex and one non-degenerate one simplex. And so the simplicial version of this has n plus one n simplices for all n. So we have the degeneracies over the zero simplex, and then we have degeneracies over the one simplex. And I'm going to order them. I'm going to call the degeneracies over the zero simplex. I'm going to call this the zeroth n simplex. And then these guys, I'm going to label 1 through n, where the one I labeled j sends coordinate the vertices 0, 1 up to j minus 1 of the n simplex to the beginning of the non-degenerate one simplex, and vertices j through n to the end of the non-degenerate one simplex. And then if you try to see what happens if you take out a vertex of the n simplex, look at the face maps. So all the face maps of this degeneracy of the zero simplex are one fewer degeneracy of the zero simplex. That's easy. Di of the degeneracy of the non-degenerate one simplex that corresponds to j is, okay, there's two cases. If we get rid of one of the vertices 0, 1 through j minus 1, then we reduce the number of coordinates that go to the vertices that go to the beginning of the non-degenerate one simplex. So di of the degeneracy corresponding to j is the degeneracy corresponding to j minus 1 if I is less than or equal to j minus 1. But if j is less than or equal to I, then the number of vertices of the n simplex that go to the beginning of the non-degenerate one simplex is unchanged. So di of the jth guy is the jth guy if j is less than or equal to I. So we try to write, but there's two exceptions. There's two situations where we take a degeneracy on the one simplex and end up with a degeneracy of the zero simplex. And that's where we split the coordinates, one in one place and the rest of them in another place. So if this is the guy I call 1, it has 0 going to the beginning and everybody else going to the end. If I get rid of the 0th coordinate, I get the degenerate simplex in dimension n minus 1. So this is the d0 of the 1 guy is the 0 guy. And here, maybe this is a more interesting example, dn of the guy I call n, I take this n away, then all the coordinates will be in the 0 simplex. So dn of the nth guy is also the 0th guy. So I can write this down. The Loday construction is going to have n plus 1 copies of A in dimension n, and di is going to always, if you look at these at these conditions that I wrote here, so di is going to fix the coordinates up to I in their place and shift all the coordinates from the I plus 1th one to the nth one down. So it ends up multiplying the ith and the I plus 1 together. And then dn, because of this, takes the nth one and multiplies it with the 0th one. And of course, you're recognizing this. This is the Hochschild homology complex. So indeed, the Loday construction over the circle, the minimal model of the circle of A is the Hochschild complex of A, and its homotopy groups are the Hochschild homology groups of A. And so what this talk is about is taking this construction that gave us Hochschild homology when we looked at the circle and looking at other spaces, and why would we want to generalize it to other spaces? So One reason is that we have the Dennis trace map from algebraic K-theory to Hochschild homology, which is the Loday construction over the circle. So you can view it from K-theory of A is the same as K-theory of its Eilenberg-MacLane spectrum. So in fact, you have two versions, one from K-theory to the Loday of A to the Loday construction of A, and one from K-theory of A, which is K-theory of the Eilenberg-MacLane spectrum, to the Loday construction of the Eilenberg-MacLane spectrum. This is topological Hochschild homology. This is a better invariant than Hochschild homology. And both of them basically involve mapping to the Loday construction over the circle. If A as a ring or a spectrum is commutative, then K of A can also be made into a commutative ring spectrum. And therefore, you are allowed to iterate. So not just look at K of A, but K of A, and so on, K of K. And so if you want to use this Dennis trace thing, you can start replacing K theory with the Loday construction over the circle from the inside out, and map the iterated K theory into the iterated Loday construction as many times as you want. But of course, if you iterate the Loday construction, this is a situation like we talked about, that if you do Loday construction of X or Loday construction of Y, that's the Loday construction of the product. So that's how Loday constructions of tori show up, and we would like to know what the Loday constructions are. And oh, this got messed up a little, but Brun, Carlson, and Dundas, they did this by studying, right, in order to understand better, to see better K theory inside topological Hochschild homology, it looks in fixed points of circle action. So they were studying fixed points of torus action on these Loday constructions of tori. Anyway, it would be good to know what the Loday constructions of tori are. Another thing is, so by now we understand ring extensions pretty well, extensions of commutative rings even pretty well. And understanding ring spectra extensions is much more complicated. So an approach people have used with Hochschild homology and topological Hochschild homology is if you have particular properties of ring extensions, such as smooth, étal, whatever, they have effects on the Hochschild homology of the extension over the base ring. And then you can use that to define analogous extensions in spectrum world by looking at the analogous behavior of topological Hochschild homology of the ring spectrum extension over the base ring spectrum. And it's clearly a wilder world. I mean, there's things that like the notion of étalness has different extensions for ring spectra. It's obviously more complicated, but it gives us a handle on classifying ring spectra. And so you would say, this is very nice, but all I used was the circle. And that's true, but we have done a lot of topological Hochschild homology calculations and learned things about extensions of ring spectra. But okay, now we've done those, and it's hard to do new ones. And if you want to explore this method of understanding the properties more, then maybe it'll be faster. I mean, while continuing to try to find more calculations of topological Hochschild homology, maybe it will be also faster to broaden the field and be able to find more behaviors that you can make analogs from. Because these methods, the Loday constructions, they work both for the for rings and for ring spectra, just like Hochschild homology and topological Hochschild homology. So we just want more examples to see how they behave. Another example, which is very interesting but calculationally difficult, is one can stabilize the suspension of the Loday construction of the n sphere into the Loday construction of the n+1 sphere, and then one can look at the limit. And the limit is something that's been known. It's gamma homology for a discrete topological Andrei-Quirin homology for commutative ring spectra. This is really hard to do because when we do these calculations, the algebra structure is quite crucial. And of course, suspension is bad for algebra structure. Nevertheless, these calculations do stabilize to something that's been known and been interesting. Okay. So we want to extend from the circle. And the easiest thing to start with once you understand the circle is the n sphere for bigger n's. And the useful thing here is that we can break down the end sphere into upper hemisphere, lower hemisphere, and equator. And the equator is one sphere lower. And because of the property I talked about when you glue two simplicial sets along a simplicial subset, the Loday construction over the sphere is the Loday construction over the upper hemisphere tensor over the Loday construction over the equator with the Loday construction of the lower hemisphere. And so that's a derived tensor of A, because of course the disk is contractible. So that's a derived tensor of A over the Loday construction of one lower sphere with A. And that gives us an E2 spectral sequence that is the Tor over the homotopy groups of the Loday construction over one lower sphere of, the pen isn't working somehow. Good. Yeah, so the Tor over the Loday construction of the lowered sphere of pi star of A into the homotopy groups of the Loday construction of a higher sphere. And the idea is that this will allow us to calculate the Loday constructions over spheres by induction. And an interesting place to start is the Einrod-MacLane spectrum of FP. And Marcel Bockstedt showed that the homotopy groups of this Loday construction, which is what we call THH star of FP, is just a polynomial algebra over FP with a two-dimensional generator. And if you start plugging this in to the spectral sequence to calculate higher dimensions, homotopy groups of higher Loday constructions. In the beginning, it's really easy because you set up this E2 spectral sequence and the differentials have nowhere to go. And so it collapses. And so you know what the thing is. And in fact, we're working over a field, so there's no additive extension, and we get very free results. So there's no possible multiplicative extension. So this is great. But then, of course, it stops collapsing for dimension reasons. And Torleif Veen showed that this spectral sequence, I don't mean to erase the frame, the spectral sequence, it collapses for n less than or equal to 2p. And so, yeah, so he used things like additional structures, and the first differential has to be an irreducible element and map to a primitive and all that kind of stuff. So he used those tools, and he got the spectral sequence collapsed for n less than or equal to 2p. So he got the homotopy groups of the Loday constructions until then. In fact, until 2p plus 1. And then Irina Bobkova and Kate Poirier and Birgit Richter and Ina Zakarevich and I pushed Veen's methods a little more, and we got the spectral sequence to collapse for n less than or equal to 2p plus 2. But then there was a thing that you couldn't rule out by dimensions reasons or by irreducible or by primitive or by anything. There was a particular differential that could be 0 and could be not 0, and we didn't know how to decide. So now let's put this aside a little. This is going to be resolved in a moment, but let's put this aside for a moment. And this question of when the spectral sequence collapses, it makes sense also to ask for discrete cases. And there are some discrete cases where the thing collapses at E2 for all n. So over all spheres, so we know the Loday constructions over all spheres to infinity. And what are these cases? So K has to be a field of characteristic P, and A can be different things. It could be polynomial over X if the degree of X is even. It could be exterior over X if the degree of X is odd, or it could be truncated polynomial over of X where the degree of X is even, but then the truncation has to be divisible by P. It doesn't have to be a power of P, but it has to be divisible by P. And also tensor products of the above cases. The point about tensor products is I'm working over a field. So the calculation for tensor product of algebras just splits nicely into the calculations for the particular algebras. So if I could do all these good cases, I can also do their tensor products. And what is special about them? Well, the Hochschild complex of these, which is the Loday construction over the circle of them, is quasi-isomorphism as a differential graded algebra. So DGA with respect to D, which is the alternating sum of the DIs, it's a quasi-isomorphic as a differential graded algebra to a formal differential graded algebra, meaning a differential graded algebra where the differential is all 0. And then you see, then if I'm trying to calculate the derived tensor of A, so say I'm trying to calculate Loday construction over a two-sphere. And so I'm trying to calculate a derived tensor of A over HHA with A. But instead of HHA and its full complicated form, I can plug in the quasi-isomorphism, the quasi-isomorphic DGA, which is formal. And so I get this double complex with the fake. I put quotation marks here. So I do it with the fake one. And if I do it with a fake one, what I'm trying to do is I'm trying to calculate the total homology of a first quadrant complex where the downwards differentials are all 0. And okay, and that's easy because then E0 is equal to E1 and D1 does something interesting, but it gives me the E2 and this thing that I had was the E2, but then E2 is equal to E infinity. So I have just calculated the Loday construction over the two-sphere of these good cases that I was talking about. And not only that, but what I got, this thing is again quasi-isomorphic as a DGA. So the homology of these good things remains good. And so the derived tensor is again quasi-isomorphic as a DGA to a formal DGA that's good. And that's stuff that I did with Bob, also with the same paper with Bobkova, Poirier, Richter, and Zakarevich. So this is good because now there are cases where we could calculate the Loday constructions over all spheres, but we are still stuck with the HFP situation. And as I said, Bookshit showed us that THH star of FP is the polynomial algebra over FP. And the spectral sequence for that I was talking about, the E2 spectral sequence for the Loday construction of the two-sphere of HFP is going to be the Tor over the Loday construction of the circle of FP with FP. And this is the easiest case in which the collapses for dimension reasons. So we get non-trivial entries only in positions 0, 0, and 1, 2. So there can't be any differentials. And we decide that pi star of the Loday construction over the two-sphere of HFP is FP in dimensions 0 and 3 and 0 otherwise. But then Mike Mendel told us that if A is a commutative augmented HFP algebra, and all these Loday constructions, by the way, are augmented, you could just collapse the whole space to a point. And so if you have a commutative augmented HFP algebra with homotopy groups FP in dimensions 0 and 8, it's connected by a chain of weak equivalences to the obvious commutative augmented HFP algebra with homotopy groups FP in dimensions 0 and A, which is you take HFP in dimension 0 and you join it with a suspension of HFP, where HFP, we know how it acts on the suspension, and the suspension part is square 0. And so, like, there aren't exotic commutative augmented HFP algebras with homotopy groups FP and 0 in dimensions 0 and A. A has to be positive. But there's another spectrum we can cook up, which will also have these homotopy groups. And here's what we do. We start with the simplicial model of the three-sphere. And then we take the free FP vector space over it, and we get a simplicial abelian group. And then and of course, the homology of that is going to be exactly FP in dimension 0 and 3. But then we also apply the Eilander-MacLean functor level-wise to this thing, and we get a simplicial spectrum. And this simplicial spectrum is also going to have these same homotopy groups. And so it's also going to be related by a chain of weak equivalences to the classic example. But of course, the normalized chain complex for this is the exterior over FP of X, where X is the class of the three-sphere, the characteristic class of the three-sphere. And suddenly we see that this is an example that we're familiar with because this is exterior on an odd dimensional guy. And So Bjorn Dundas and Birgit Richter and I showed that basically all these guys have these same E2 spectral sequences trying to calculate the Loday construction over the 2-sphere based on the Loday construction of the 1-sphere. And for the exterior guy, the spectral sequence collapses, but then we can map isomorphically the spectral sequence for the simplicial abelian guy to the exterior guy. And so this one also collapses. And then also we can use the collapse of the spectral sequence for the simplicial abelian group to get collapse for the spectral sequence for the simplicial spectrum. And then we can use all the little weak equivalences. They define equivalences of spectral sequences for various spectra. So basically, if the spectral sequence collapses for this guy, then it for this guy, then it collapses for this guy. Then it collapses for this guy, and then it collapses for THHFP. So we can do Loday construction over a 2-sphere, or sorry, over a we're working with the Loday construction over the 2-sphere. So now we're trying to calculate Loday construction for this 3-sphere. So we've just found out the Loday construction of over the 3-sphere of HFP is what you'd think would be given to you if the spectral sequence collapsed. But then once you got this, you're somehow in the world of the collapsing examples. So you can replace the next level by B of FP with the exterior over FP of the 3-dimensional guy and FP. So you're in the machine. You have just joined the world of the good discrete examples. And so we can calculate, so we get the spectral sequence collapses, yeah, for this, for that, for the Aaron-MacLean functor, for this, it does for this. And we got all the Loday constructions over all spheres of HFP, but it turned out that Maria Bastera and Mike Mandel already knew them. But we could tinker with this construction and make it slightly more complicated and get the Loday construction over higher spheres of the Aaron-MacLean spectrum of Z with reduced coefficients in HFP. So we didn't discuss Loday constructions with reduced coefficients, so if you have a pointed simplicial set, the idea of Loday constructions is you took a copy of the ring over each simplex, but now the variation is over the base point and all its degeneracies. We're not going to put the ring, we're going to put a module of the ring. And because all the degeneracies and face maps of the base point remain at the base point, the module is going to stay there. And whenever other things want to get multiplied into the base point, we know how the ring acts on the module. So it's like reduced coefficients. I mean, the whole thing of Loday constructions is really a multiplicative analog, right, of the simplicial chain complex. And so you can look at it as if you put different coefficients on the base point and everybody else had the same. So we get this. This is definitely simpler. So, of course, the Loday construction of HZ with coefficients HFP is the same thing as if I did the Loday construction over HZ, and I smashed it over HZ, where HZ multiplies into the copy of the HZ over the base point. Smash it over HZ with HFP. So we know the homotopy groups of that. So this enabled us to compute pi star of the Loday construction over S2 of HZ just by trying to find the orders of the p torsion, but it was complicated. And we started to try to do this for the 3-sphere, and it was a little hard. So we didn't do that, but we were able to, I mean, this thing goes through if you replace Z by any numbering and FP by the numbering quotiented by some prime ideal. But somehow reducing to coefficients in a prime ideal makes the calculation much easier. Okay. And then I was saying we might be interested in tori. And here's a strange fact. For some commutative rings or ring spectra K, and some commutative unital K algebras, and absolutely not all, we have this strange situation that if the suspension of the realization of X is homotopy equivalent to the suspension of the realization of Y, the Loday construction of X has the same homotopy groups as the Loday construction over Y of A. So truly a strange property, and not clear why we would expect this thing, right? Because it's supposed to be a homotopy invariant of the homotopy type of X, but of course we have very non-equivalent spaces whose suspensions are homotopy equivalent. So yeah, if we get this, we call this that A is stable over K. And this is a very useful property because this is a very useful property because for any X and Y, the suspension of the product is homotopy equivalent to the suspension of X join the suspension of Y join the suspension of the smash product. And it's I'm very happy to calculate Loday constructions over joins of spaces because that's the simplest gluing thing. The subcomplex I'm gluing on as a point. Loday construction over a point is A. So the Loday construction over V join Y of A is just the Loday construction over V of A tensor over A with the Loday construction over W of A. So if A is stable over K, and we knew the Loday construction over all spheres of A, we could calculate for all tori. So for example, for the two torus, right, it's the product of S1 cross S1. So the suspension of it is the same as the suspension of S1 join S2. And we could keep on going and get the suspension of an N torus is equivalent to the suspension of this big join of spheres. And we'd be done. So Dundas and Tenty said that if we take the symmetric free K algebra on a simplicial set W, eKW, that's stable over K. So even W being finite, like W a point or endpoints, Kx or Kx1 through Xn, that's interesting. So like free things are stable. And the idea is if you take Loday construction over X of eKW, it's the same thing as the Loday construction over W of eKx. Because in degree n of the diagonal of the bisimplicial set here, if you take this one, if you take this one, then you have a tensor over EKWN, but that's the same as EKXN times WN. Each generator WN that comes from the coordinate of XN could be regarded as a generator corresponding to that XN and that WN. But then, of course, you could group it the other way. And this EK of X is the free K algebra on the K module KX. And the K module KX is the product of the Eilenberg-MacLane spaces K, HN, XKN. And so it could just be entirely reconstructed from H star of X with coefficients in K. But of course, the homology is preserved by going to the suspension. So if the suspension of X is the same as the suspension of Y, I know that the homology groups of X and Y are the same, and therefore I know that Kx is the same as a homotopy equivalent to Ky, and I get the same free guy. And with Alice Hedenlund, Sarah Klanderman, Birgit Richter, and Foling Zhu, we did an analogous result for K commutative ring spectrum and M a K module and PKM, the free K algebra on M. So it's going to look like this join of all these powers modulo the symmetric group. And the point here is that the L over X of this free guy is like the free guy over X plus smash with M. But that's, of course, this spectrum is, of course, the suspension spectrum of X plus smashed with M. So, of course, it depends only on the suspension of X. So again, it's not X that goes into the calculation. We can just have suspension of X go into the calculation. So, and localizations and Natal extensions of stable algebras are stable. So smooth discrete K algebras are stable over K. And Yuri Berest and Ajay Ramados and Wykit Young showed that if K is a field and H is a commutative hop algebra over K, so not that many, but if it is, then H is also stable over K. And the idea there is that by one of the properties of Loday constructions, commutative algebra maps from the Loday construction over X of H to a commutative algebra B is in bijection to continuous maps between X and maps from H to B of commutative algebras. But and if I want, this has a one-to-one correspondent with wanting pointed maps and adding a base point to X, because the base point has to go to the zero map. But because H is a Hopf algebra, map HB has an E1 multiplication structure. And then maps, topological maps from some base thing to an E1 algebra is in bijection to E1 maps from the free E1 space on that thing to the map HB. But the free E1 space on X plus is loop suspension X plus. And suspension X plus could be made from suspension X. I should have said that also in the previous example. So again, it's only dependent on the suspension. And with Hedenlund, Klanderman, Richter, and Zhu, we generalize this to commutative Hopf algebra spectrum. And there's other examples. So with Birgit Richter, we showed that if your algebra that you're looking at, if your ground algebra is A, and what you're doing is, your extension is a, oh, I should have said here. Oh yeah, no. So you're doing a Loday construction over a smaller K, over a suspension, it has to be a suspension of A, then this whole thing is stable over A. So it's a little confusing because you have to do Loday constructions over A and over K, but fundamentally you end up using the fact that you're relating this to Loday construction over suspension of Y smashed with X, but that can be viewed as Y smashed suspension of X. So this is a kind of example of stable things. And if R is a discrete commutative ring and A is a regular element, then R mod A is stable over R. And then we can use induction and iterate this, and you have a discrete commutative ring and a regular sequence. So the quotient by the regular sequence is going to be stable over R as well. And then we were also able to show that if you have the Anver-MacLane spectrum of a quotient of a very commutative ring by a regular element, and you want to join it by a suspension and a suspension of that quotient, that is also stable. So, but this is obviously a weird property, right? And Dundas and Tenty didn't have to go very far to find counterexamples of things that aren't stable. So their example is the very non-exotic ring QT over T squared, and it's not stable over Q, because even on the 2 torus, they showed that, so if it had been stable, right, the construction over the 2 torus would be the same as the construction over circle, join 2 sphere. And it's not. The Loday construction over the torus is smaller. So they didn't have to pick a very exotic ring, and they didn't have to go to a very high torus to show that it's not. And this example is sad, not because we expected this to be universal, but because it shows that stability is not a transitive property, right? Because QT is stable over Q because it's free. And QT mod T squared is stable over QT because this is a regular element. And yet QT squared is not stable over Q. So it's hard to, and by the way, we came up with, because this notion is so unnatural in a way, we came up with a lot of weaker notions that we could prove in various little places. But there's no notion of stability which would say that QT mod T squared is stable over Q. Because we could do it over algebras in terms of dimensions, additively, multiplicatively, only in settings of products. There's a lot of weakenings, but none of them would admit this. And then with Hedenlund, Klanderman, Richter, and Zhu, we showed that QT over Tn is not stable over Q. And just like Dundas and Tenty caught their example with T squared as being unstable on the two torus, we catch our example as being unstable on a higher torus, on Tn. I mean, I sort of think, we haven't formalized this, but I think of it as if n is bigger, right, the ring is a little closer to being smooth. So it behaves a little better in terms of stability. Then in his thesis, where he showed the calculations over spheres, he shows that HFP behaves well, as if it were stable, over the sphere spectrum on tori Tn for n less than or equal to P. And we're hoping to show that it keeps on going, but we've tried all sorts of methods, and we're working on some still, but we haven't shown it yet. We would like to show that it is, but whatever. Anyway, thank you.